Hello. In this video, we're going to be exploring a simple mechanical setup that seems to defy gravity. So we have this V-shaped track that has two rails that are diverging and is at a slight incline from the surface. And we have this double cone shape. And if I put the double cone on the track, it moves up as opposed to moving down. If I try with other objects, for example, this cylindrical can, it moves down, as expected. But with the cone, it moves up. And this was actually first set up by an English mathematician named William Laybourne. I believe it was in 1694. And he called it a mechanical paradox. And in this video, we're going to be exploring and analyzing why this is happening. Now let's do video motion analysis. We will be using Pascal for this. On the left side, we have our video. We have our coordinate system embedded into our video. And we have these red crosses that are going to be tracking the movement of the cone, the double cone, as it goes up the incline. On the right side, we have our graph. So our graph is going to be graphing the motion of the double cone, and our y-axis in this case is going to be the y position, which will be the height, and is going to be plotted against time. So this will give us the change in position over time, the change in the vertical position over time. And we fast forward, C is tracking the movement of the cone and is plotting it on the graph. Once we're done, we can zoom in. We can do our linear fit. Now this means that our cone is actually moving downwards and not up. And we can kind of make sense of this. So if we go up to the beginning, we can see that most of the cone's body is on the surface of the two rails. So it's above the incline. But as it moves, it's almost as if the middle part of the cone is falling in between the two rails. And like by the end, towards the end, you can see almost half of the cone is under the two rails. And so even though it looks as if it's going up the incline, the center of mass of the cone is actually going down. You can see in the beginning, it's at the top of the incline, the top of the two rails, but as it moves along it, it slides in between those two rails, and the center of mass ends up in a lower position. Now we're ready to express the design of our setup mathematically. Here we have three views of the setup. Figure 1 is a side view, which is the vertical section of the setup. This figure 2 is the front view. This is as if we're viewing the double cone from the front. And we have P and Q are the contact points where the cone contacts the rail at this point. And P1, G1, and Q1 are projection of those 3 points, where G is the center of mass. And in figure 3, we have a shadow projection of the whole setup to the ground. And so these dotted lines right here are the rails. Beta is the angle, the half angle between them. And as the same with the figure 2, we have P1, G1, and Q1. Now, let's start with figure 3. If we look at figure 3, we can easily get the tangent of beta, which will be P1, the distance from P1 in G1, divided by the distance from G1 to the origin. However, we can see from figure 1 that the distance from the origin to G1 is basically x. And so we can replace that, and now we have tan beta will be P1 G1 divided by x. And the distance from P1 to G1 is half of the distance from P1 to Q1, which will give us P1 Q1 over 2x, and P1 Q1 is equal to PQ. And so now we have the expression for PQ, which is 2x tan beta. For figure 2, we've introduced two more variables to help us express the tangent. So S is a point in between G and R that lies on the same line as P and Q, and R is the bottom of the cone, the double cone. That's the big R, and little r is the radius of the middle part of the cone. And doing this, now we can see that the distance from R to S divided by S and P is going to be equal to tangent of theta, where theta is the angle between the straight line and the slanted part of the cone. And with this, we can get RS equals SP tangent theta. But if you look, SP is just PQ divided by 2, and we can plug that in. And we know PQ is, from figure 3, is 2x tan beta, and we can plug that in. And now we have expression for SG, because SG is basically RS minus the radius, the radius minus RS. And now we have R minus X tangent of beta, tangent of theta. And if we look at figure 1, we can see that our y of X is SG1, the distance from S to G1, plus the distance from S to G. So the distance from S to G1 is this distance, plus the small distance at the top from S to G. And now we have our SG. If we can calculate SG1, then we can have the expression for our y, and we can do that. We can notice that SG1 minus A divided by X equals to tangent of alpha. So the alpha is the angle here, and if we take the tangent of it, that's going to be SG1 minus A divided by X. And from there, it's pretty straightforward. SG1 is going to be A plus X tangent of alpha, and from there we can get our y. Just we have this long expression. We can simplify it, and since A and R are constants and y is a function of X, so the gradient will be tangent of alpha minus tangent of beta multiplied by tangent of theta. And so for our setup to work, the gradient, the slope, must be negative. And from what we saw in the video analysis, that has to be true. And so basically what we found is whatever theta, beta, and alpha we plug in, the end result must be negative for our setup to work. And so this is a good result for design. So if we want to design a setup, a double cone setup, we just have to make sure that our angles have this relationship. And now we can check the dimensions of our setup, because we know our setup works, and check if they meet this condition to make sure that our calculations are right. And with this result, we can easily verify that our setup had the correct dimensions. And so I measured the 3 angles of my setup, and as you can see here, we got the result to be negative, negative 0.025, and this indicates that tan alpha is less than tan beta multiplied by tan theta, and that is all the conditions we need to meet to make sure that our double cone is going to be rolling uphill. Before I end the video, I want to quickly share my attempt of trying to express this using the Lagrange method. I don't have much time, so I'm just going to keep it quick. You're welcome to pause the video and try to analyze it. But I started with 1 degree of freedom and 1 generalized coordinate along the rail path. Then I described my radius using that the radius on the contact points using the generalized coordinate. The same thing with the height change of the center of mass. And then from there I was able to get my kinetic energy and potential energy. The kinetic energy has 2 parts, rotational and translational. And from that point on, it's just a lot of math, a lot of algebra, trigonometry. And at the end, I ended up with this humongous differential equation that I couldn't get much information out of. So I'm just going to stick to this solution.